Good morning, good afternoon, good evening, everyone. I'm glad to be here to share our recent research in self-supervised learning called Self-Supervised Learning Disentangled Group Representations as Features. As it's a recent conference submission, you can consider my talk as a trader. Please keep tuned and check our website for the fall piece in late September. The self-supervised learning first learns a generic feature representation, for example, a feature backbone, by training with unsupervised pretext tasks, such as a prevailing contrastive objective. And then the above stage 1 feature is expected to serve various stage 2 applications with downstream fine-tuning. So, what does SSL learn? Features. How does SSL learn? Contrastive loss. But why does this pipeline learn group features? To answer this question, we first need to know what is feature. We are interested in a more fundamental definition of feature. Features represent the semantic meanings of the world, and the difference between two features reflects the semantic change. Say, how to change from dog to cat. Furthermore, if this change is equivalent with the feature, this feature is a valid representation of the change. This actually belongs to the group theory. For simplicity, you can consider the group as a set of verbs acting on these images. For example, a group action can be painting an image from red to green. So, how to embed this group action? We first start from one group action and still use the color change as the example. The key is to first collect the training data affected by the group action. Inspired by the Katie theorem, any group is isomorphic to a permutation group or its subgroup. In our example, the permutation is a kind of sample sorting, from a random sorting to an n-order sorting. Red digits are moved to the left, while green digits are moved to the right. Then we simply divide such samples into two subsets. Here comes a partition. Given the data partition, we need a learning objective. Besides the conventional contrastive loss, we also have the invariant risk minimization loss, which regularizes the loss to be invariant across different subsets in the partition. To achieve this invariance, the model needs to decompose a separate feature subspace to encode the color semantic, thus isolate the effect of the color across different subsets. In this way, color semantic is recognized and learned. This learning objective is also named as minimization step in our work. After introduction how to learn one group action into the feature, now we can answer the question, can we achieve a good feature in general? SSL should learn to embed all the semantics, and these semantics are disentangled in vector space. We name this as disentangled representation. In general, we propose a classic road model of visual representation to define the disentangled representation using group theory. The disentangled has two concepts. First, equivariant. This was discussed just now, that is, changing the semantic red to green in the U space is equivalent to change the color vector in the X space from the value encoding red to green. Second, decomposable. For example, changing the color semantic does not affect the digit vector in the X space. Recall that we have introduced how to disentangle one group action in the feature space using the minimization step. Similarly, the key to disentangle another new feature is to find a new partition set. Let's think reversely in an informal but intuitive way. If we can learn one disentangled feature, then we can minimize its objective. Its contraposition is that if we maximize the objective, we can find an entangled feature. We proved that the argmax P is acted by a group action whose representation is not disentangled. Then these two steps can be iterated until convergence. For example, as shown in the left figure, the discovered partition is based on the group acting on the color semantic. Subset number 1 is almost green, while subset number 2 is red. Note that our maximization step can be considered as an active causal intervention of the data, which is fundamentally different from the conventional statistical learning that are proved unable to disentangle features. Can existing SSL methods lead to the disentangled representations? The answer is no. On the left-hand side, we compare the representation learned by the same clear and our iperm algorithm on STL10 dataset. We report the KNN classification accuracy using the augmentation equivalent features and the augmentation unrelated features, respectively. We can find same clear mostly contributes to the first part, demonstrating that the other part is still useless as the features are still entangled. On the right-hand side, we show the image semantics captured by the features of the CNN backbone. For the rightmost example, such as a building image, our iperm representation at the 29th layer roughly disentangles the rectangular building, the stairs, the cylinder, monuments, and the side buildings into different feature maps, while same clear entangles all of them. The left figure visualizes the features learned by the same clear and our iperm on the colored and list dataset. For same clear features, it is obvious that there's no clear boundary to distinguish the semantic of the colors in the same clear feature space. Besides, the features of the same digit semantics are scattered in two regions. For our iperm, the features are well clustered. The feature space has a symmetric structure for each individual semantic, validating the decomposable property of iperm representation. We also explore how does iperm disentangles features. This visualization corresponds to the maximization step. We can get the following conclusions. First, for example, in partition 1, red and green digits are separated. Besides of the obvious semantics such as the digit and colored, labeling the first line and the second line, we can also discover a new semantic, the slot. In this figure, we aim to visualize how equivalent each feature dimension is to the change of each semantic. The dark color shows that a dimension is more equivalent with respect to the semantic indicated on the right. We can see that same clear fails to learn the decomposable representations. In contrast, iperm achieves disentangled representation by representing the semantics into separate dimensions. On both color and list and shape 3D dataset, iperm significantly outperforms same clear regarding all the metrics. We demonstrate our results and compare with baselines in both tables. Incorporating iperm to the three baselines brings consistent performance boosts to downstream classification models in all settings on all datasets. To sum up, our community has already reached the agreement that self-supervised learning is very useful, but we still hunger for a definitive answer why it works. I hope our work using group theory as a fundamentally different point of view can help you get closer to the truth. End of my talk. Thank you very much.
Hi everybody, I'm Yuwang Wang from MSRA. I would like to introduce my research work, Learning Disentangled Representation by Discovering Pretrained Generative Model, a Contrastive Learning View. Bender pointed out that for AI to understand the world fundamentally, The only way is to identify and disentangle the underlying explanatory factors of the observed data. Given observed images of 3D sense, for this toy example, the underlying explanatory factors are the camera pose, object shape, and so on. With those factors, we can generate and control the images with these disentangled factors independently. For disentangled representation learning, the goal is to learn to extract such representations of the factors from the images. Here is a toy example. We have the ground truth of factors, but for real-world data, typically, we need to learn disentangled representation in an unsupervised manner. Disentangled representation learning is important for both fundamentals and applications. For fundamentals, it can help the interpretability, reasoning, concept learning, and so on. For applications, it can benefit controllable generation, editing, domain generalization, and so on. For example, given a dog image with disentangled representation, it is possible to control the images according to the text, make the dog happy, make their eye bigger, while keeping other attributes the same. Disentanglement is raising a lot of attention, and there are increasing works on it. It is one of the top 50 keywords in this year's ICLR submissions. Let's revisit some of the milestone works in this literature. The conceptual definition is proposed by Benjer in 2013. After that, to achieve unsupervised disentanglements, some works tried ad hoc implementation by adding an extra disentanglement regularization to generative model, such as VE or GAN. For example, the regularization in VE-based model is a total correlation of the latent variable distribution. However, this regularization results in a trade-off between the disentanglement and the generation quality. Then in 2019, SML best paper challenged these methods and pointed out that only the regularization is not enough to achieve unsupervised disentanglement. How to achieve unsupervised disentanglement is a challenging task. Fundamentally, these methods try to fulfill three tasks simultaneously. The first one is discovering the generative factor, and the second one is learning a generator or decoder to generate images from generative factors. And the third one is learning an encoder to encode images to disentangled representations for these factors. So the fundamental is that we do these three tasks together and we have a trade-off. So it is possible to do these three tasks separately and get rid of the trade-off. We propose DISCO to learn disentangled representation by discovering pre-trained generative model from a contrastive learning view. DISCO is inspired of some previous work. Given a pre-trained generative model without any disentanglement regularization, when traversing along different directions in the latent space, the generated samples show different variations. This indicates that there are disentanglement properties embedded in the latent space. If we can find the directions of distinct image variations, for example, one changes the background color and one changes the object color, then according to the goal of disentangled representation learning, the directions can be treated as factors. To learn the disentangled representation, we use the encoder to extract the representation from the images. DISCO provides an alternative route for disentangled representation learning. Instead of doing the three tasks simultaneously, we leverage the pre-trained generative models with high generation quality and focusing on jointly discovering the directions in the latent space and learn disentangled representations. From the contrastive learning view, starting with the image variation of pre-trained generative model, we have a more effective way to achieve disentangled representation learning. Here is the framework of DISCO. Given a pre-trained generative model, we fix it. Then we use the navigator to discover the directions in the latent space as the factors to generate image variations between the image pairs. Then we use the disentangling encoder to extract the representation from the image pairs. To model the variations between the image pairs, we build the variation space based on the encoded representations. By pulling together similar variations and push away different variations, we jointly train the navigator and the encoder to make the navigator discover distinct directions and the encoder extract disentangled representations. By leveraging the pre-trained generative model in this way, we ensure the high generation quality and do not have the trade-off between disentanglement and generation quality. Here is the quantitative results. DISCO achieves the state-of-the-art disentanglement on 3 popular datasets and 2 disentanglement metrics. DISCO can also work for the current majority generative models, include GAN, VAE, and FLOW. Compared with the previous methods, due to getting rid of the trade-off, DISCO has much better image generation quality and achieve better disentanglement at the same time. With DISCO, we can control the overexpose of a photo or make her face smile, while keeping other attributes the same. For cat image, we can change the color of the cat to be black or make their eyes smaller. Here is the evaluation of the discovered directions. We achieve the state-of-the-art result compared to other latent discovery methods. To verify that the variation and the contrast is the key for DISCO, we do the ablation study by replacing variation with concave operation or replacing the contrastive loss with classification loss. The performance drops a lot. Only with contrastive loss on the variation space, we can better discover the generative factors and learn disentangled representations. As a conclusion, disentangled representation learning is a fundamental task, which is a key for general AI and can benefit a lot of applications. Disentangle leverage pre-trained generative models and propose a contrastive learning view for disentangled representation learning. Currently, our method highly relies on the disentangled property of the latent space of the pre-trained generative model. The next step is to demystify the disentanglement property in pre-trained generative model and achieve better disentangled representation learning. That's the end of my presentation, and thanks for your time.
Hello everyone, I'm Shujian Yu, a faculty member at the UIT, the Arctic University of Norway. I'm also affiliated with the Norwegian Visual Intelligence Center. It's my honor to have the opportunity to present our work, Making Deep Neural Networks Transparent by Information Theory, at the Microsoft Research Summit 2021. This is a joint work with my supervisor, Dr. Josie Principe at the University of Florida, and my colleagues at the UIT, the University of Kentucky, and the NEC Labs Europe. We know that the deep neural networks are all around us. We have successful applications in self-driving cars, in speech recognition, in energy analytics, and in healthcare. However, it has been a long time that people claim that deep neural networks is a black box because there are only a few theoretical observations to explain their great success. So, indeed, there are still some fundamental problems concerning the deep neural networks. For example, the interpretability. Questions include, why did a trained deep neural networks reach a certain decision, or which components of the input do contribute most? On the other hand, we also want to understand the generalization behavior or a deep neural network when it was trained from scratch. So questions then include, why do deep neural networks perform very well, or how to improve the generalization ability of deep neural network to out-of-distribution data? Our work in the last few years focused on using the methodology of information theory to answer questions above and or try to give some insights to the above questions. Currently, the information theory has gradually become popular methodology in various machine learning or computer vision tasks, and the popular examples include to use information theory to explain or identify the most influential feature or data to the decision, or understand the general behavior of deep neural networks in the training phase. Example include the information bottleneck theory, or identify the fundamental properties or derive a tighter generalization bound of deep learning, or figure out the inner working mechanism behind deep neural nets, such as the principle of rate reduction. So in this talk, I will briefly introduce some of the work from our group in this area. In order to apply information theory to various machine learning or computer vision tasks, the most important or first step is to have a way such that we can effectively quantify information theoretical quantities such as entropy or divergence, only from samples. This is just because the traditional Shannon's entropy functional such as the entropy, the divergence, or mutual information are all defined over the probability distribution function of the data. However, we know that in most of the cases, the distribution of data are unknown. And moreover, to the effective estimation of the probability distributions in high-dimensional space is a very, very hard or even infeasible problem in either machine learning or statistics. So our question is that if it is possible to estimate information theoretical quantities such as the divergence, mutual information, or entropy without resorting to the estimation of the underlying probability distribution, the answer is yes. In our recent work in transaction on information theory and transaction on pattern analysis and machine intelligence, we defined the matrix-based entropy functional, and we show that we can define entropy or mutual information or divergence just use the eigenspectrum of positive definite matrix generated from given samples. For example, if we want to estimate the entropy or total uncertainty of variable x, suppose I have n samples x1, x2, and xn. Each xi is in d-dimensional space. So instead of evaluate its underlying probability distribution px, what we did is just to first evaluate a gram matrix K of the size n by n, and we show that we can define the total uncertainty or entropy of X just to use the eigenvalues of the normalized gram matrix A. In our recent works, we also show that the matrix-based entropy functional is automatically differentiable, which means that it can naturally be embedded into a deep learning for the training or some other tasks. Now, based on the state-of-the-art estimators on entropy and mutual information, we begin to use information theory to explore some fundamental properties behind deep neural networks. So, the most famous information theoretical principle in deep learning is the information bottleneck. Given input X and the desired output Y, the information bottleneck formulate the learning problem, as a trade-off between maximization between the mutual information of Y and T minus the beta of the mutual information between X and T. The first term, the mutual information between Y and T, can be understood as a sufficiency, or the predictive performance of T on task Y. On the other hand, for the second term, the mutual information between X and T can be understood as the complexity of the representation of T. So with the state-of-the-art, the matrix-based entropy functional, we measure the mutual information values between xt and between y and t in the training of deep neural networks, and we plot the information plane. The x-axis of the information plane is the mutual information between x and t, and the y-axis of the mutual information plane is the mutual information between y and t. The dark blue point here is the mutual information values at the beginning of the training, and the green point is the mutual information values at the middle of the training, whereas the yellow point here is the mutual information values at the end of the training. And we can see that there are obvious two phases in the training of deep neural network. In the first phase, the mutual information values increase drastically. However, in the second phase, the mutual information value, especially the mutual information between x and t, will begin to decrease, which means that there is a natural compression for the latent representation. And although this observation, the fitting phase and the compression phase is still a controversial issue in the community. However, based on our recent studies, based on the metrics-based interfunctional, and the results from our peers, we gradually believe that this phenomenon is common to deep neural networks and especially for the convolutional neural networks. On the other hand, we want to say that the information bottleneck principle also has its practical usage on applications, including the interpretability. For example, in the problem of salience detection, we can just imagine T as the most informative component to our decision Y. Similarly, for the problem in natural language processing, if we want to explain based on the sentence, I cough a lot at night, to decide if I have a flu or not, then I can just generate a binary mask and then put the mask on the sentence of the X to generate a compressed representation which only contains two most informative words, cough and night. Only based on the two most informative words, cough and night, I can decide if it's a flu or not. In our group, we also use information theory to improve the generalization performance of deep learning. For example, for the problem of classification under covariance shift, which means that the distribution of X changes, but the distribution of Y given X remains the same. We have proved and validated that if the distribution of prediction residue Y minus Fx is independent to the distribution of X, then a model is robust against covariance shift if and only if such criterion is satisfied. Moreover, we also prove that this loss function can also encourage the model is robust against noise in the label. In our recent work, we also show how to use information bottleneck principle and how to learn a discrete or soft mask on the raw features such that it can progressively drop out the spurious correlations and only remains the causal attributes in our data set. Such a mechanism can also improve the generalization of deep neural network in sequential environment. The conclusion of my talk is that we have proposed a matrix-based interfunctional, and we show how to use it in understanding and generalization of deep neural network. However, we also want to say there are many other more opportunities to use information theory beyond information bottleneck, such as the principle of rate reduction, the rate distortion functions. Thanks.